Hey everybody. Uh Gavin, Graham, are you there?
Oh,
Oh.
hey, Marisa.
Oh, hi Graham. So
How
nice
are
to see
you? Oh,
you.
it's great to see you too.
Where's Gavin? Is he here too?
Oh, shoot. I must have lost him back at Mare Imbrium. Uh, we were out here exploring the moon to get ready for our Rockin Pop-Up, but I'm sure he'll catch up.
He's
Uh,
probably fine.
he's fine. He knows his way around these parts.
Yeah. Cool. Okay, great. Well, this will be our first Rockin Pop-Up with just one geology gent. I don't know how I'll manage. But
Marisa, to be honest with you, I don't know how I'll manage, but we're gonna get through it.
Whew, okay, yeah. I think it'll be okay, and hopefully Gavin is fine and not lost in a mare somewhere. Um, Great. So yeah, we're talking about the moon today for the Rockin Pop-Up, and I guess just for all of you joining us out there, I'm Marisa. I'm the public programs manager at the Santa Cruz Museum of Natural History, joined by the better half. No, I shouldn't say that.
Just
You're
a
both
half.
you're both the best. Half of the Geology Gents, Graham, and also happy belated World Geologists Day,
Oh my gosh.
Graham.
Thank you so much. I actually saw your post and it brought quite the smile to me. So thank you for recognizing us. We both feel very honored.
Yeah, well, always happy to celebrate you too. And we'll give extra celebration to just you this time, since you're okay. So we're gonna be talking about the moon today, and I'll do my best to maybe be your other half for this
Awesome.
one, so that you have someone to talk to and you don't feel lonely.
Great. Thank you so
Okay.
much. And yeah, we are in great company today because we're going to be talking about the moon. So just give me a second and I will get us started. The moon. So yeah, the moon is incredible, right? It's like it's a part of our everyday life, and yet it's like this mysterious thing up above us. It took, people have been fascinated with the moon for all of human history. Only within the last 100 years have we been able to put someone on the moon, much less than 100 years. And so, yeah, let's dig a little into this awesome mystery in our backyard. So the moon. I want to start by, we talk about all this stuff, taking rockets to the moon, trying to bring things back from the moon, putting all this instrumentation out on the moon, but we can learn so much by just looking at the moon up in the night sky.
Yeah, one thing I know about the moon is that there is a man that lives on the moon because of what I can see, right? Isn't that
Yeah. So the great patterns on the moon, right? The man on the moon, the holes of the Swiss cheese that is the moon. It's that we've got these dark parts of the moon and these light parts of the moon. And so before I started spending a lot of time thinking about the moon as a geologic body, as a planetary body in our solar system, I always thought these dark and light spots had to do with shadow, but they're actually rock types. And so just by looking at the moon, we can actually see that there are these different sort of colors to the moon, these different sorts of rock types that are forming on the moon. Just like, we can kind of tell the different parts of the earth, right? We've got these blue parts that are water. We've got these, kind of beigeous, rocky, sometimes they're covered in green parts that are the land. And so just like that, we can look up at the moon and see these two different rock types, one dark type and one light type. And already there, we know that the moon's geologic history had at least two steps in it, right? We didn't just make one rock, we made two. So two things must have happened.
That's wild. I really thought that it was more of a topographic indicator than like a material indicator. This
Yeah,
that blows my mind, but it
mine
makes sense.
Mine too, yeah. And the trick there is that, right, because we know the moon goes through its phases, we know that the orientation of the sun to it is changing, yet the position and shape of those little dark spots never change. And the other neat thing about those dark spots, and this is a little bit harder to see with our naked eye, and it helps if we can look at it with a telescope, but even from here, we can see that these dark spots, they're round. And really the big thing that makes round shapes on planetary bodies in our solar system is impacts, these things getting whacked by meteorites. And we do know that Earth has been hit by meteorites in the past. We know that there are these impact craters on Earth, but they're really hard to see. They're really hard to find. They get filled in, things grow on top of them. Basically, the processes of erosion are really punishing to craters. They cover craters up really quickly on Earth. And so the fact that the moon is covered in these things means it must have less erosion than Earth. And I know some of you may be thinking, well, Graham, maybe the moon just gets hit by more meteorites than Earth. The trick there, though, is that the moon is right in our neighborhood, right? The moon and the Earth are always hanging out together. The moon isn't in the grand scheme of our solar system, the Earth and the moon are real close. And so the moon should not be getting hit by anything more than the Earth is. So it really does mean that our moon not only had 2 events in its geologic history at least, but today erosion is really, really slow.
Do you know, like, for the craters on Earth, even if they're not as easily visible, do we have a sense of if they're similar in size to those that are on the moon? I would assume so, right?
Yeah, so a lot of them some of them are really big. Some of them are pushing the size of some of the craters on the moon. The thing with craters on Earth, though, is it's kind of twofold. Is that one part is that craters on the Earth tend to get filled in pretty quickly, so we don't preserve really big ones. And then the other big trick is that our Earth has plate tectonics. We're losing ocean crust all the time. We're reshaping our continents over Earth's history. And so over the history of our solar system, the number of impacts, big impacts, has gone way down, right? Our solar system had this really chaotic beginning, and it's been a little bit quieter since. And since that chaotic beginning, when a lot of these formed on the moon, the Earth's surface has totally been reworked and remade by plate tectonics. So once there were definitely craters that big on the Earth. Today, those really big ones, not so much. All we're left with are smaller, younger ones.
So we're not seeing the full impact history on Earth, but we do see pretty much the full impact history on the moon because it just hasn't, once they're there, they're there.
Exactly.
They don't go away. Okay.
Very well said. Cool. So now let's zoom in on these craters, right? We've seen what we can see just from our own backyard. Now we'll send a satellite over there and we'll take some images. And so we get up close on those little dark spots. Those are called mare or maria in the plural. And those are these dark sort of basins on the moon. And they were called mare because that's the Latin word for sea. And we'll come back to that. But yeah, they're these dark, low-level space. The original astronomers or early astronomers who had first started looking at these with telescopes saw those and thought they were the ocean. They thought they were oceans on the moon. We now know that they're not oceans. They're filled in with a dark rock. And then up on higher ground, there are light rocks that make up the lunar highlands. And so let's take an even closer look at each of these and think about how they formed. So I mentioned that these were named after seas. They were thought to be oceans. They were filling in low levels on the moon. So naturally, that would make sense. Our oceans are in the lowest points on Earth. But the lunar maria didn't form from oceans of water. No, these formed from oceans of lava. So way back when, over 3 billion years ago, the moon had a really rough time and what a lot of folks have called the late heavy bombardment. And this is kind of a contentious topic in planetary sciences, but we know that at some point in Earth's history, or in the moon's history, there was a time when big meteorites, big asteroids were just walloping the poor thing and making these really deep craters. And with those big impact craters, it would push down into the moon's mantle, shatter a bunch of rock, and then rebound back up. And so as those cracks start opening back up, this made volcanoes. And so imagine like if we were to take Hawaii, like where we've got volcanoes on Hawaii, or we just took like Kilauea on Hawaii, and that's what this picture I believe is of, a lava flow out of Kilauea, but basically made a lava flow about the size of California. And we just start filling in this lava lake out of this deep crater. That's how these Maria are forming. We're forming these big basalt seas, and those are filling in. So, you know, those astronomers weren't that far off when they called them Mare or Maria. Okay, but we've got this lava down in the low elevations. That means, and they formed from volcanoes, and those volcanoes needed to form on something. So what were those? Those were the lunar highlands. And these are way more ancient than the Mare, or they're just more ancient than the Mare. They're a lot older. And these formed in the ancient lunar magma ocean. And so you all heard me right. When the moon was first forming, it was a giant ball of magma, or lava if you're on the surface of it. But one way or the other, the whole thing was liquid. The whole thing was hot liquid rock. And I think that's pretty awesome. But as all hot rock does, it cools down. And as it starts cooling down, things start crystallizing out of it, just like in a magma chamber on Earth. And those first things to crystallize are pretty heavy. They're minerals like olivine and pyroxene, and those start sinking to the bottom of that ocean. And that's what starts making the moon's mantle, right? Above this little metallic core, we start sort of filling in a mantle as we're raining olivine and pyroxene crystals down out of this ocean. And then as this magma continues to evolve, it starts crystallizing other things, most notably the mineral anorthite. And anorthite is actually buoyant. Anorthite is kind of related to feldspars, which are the light colored minerals in granite, a little bit different, but this stuff is really buoyant in a lava. And so this actually floats up to the top. And we start making these anorthite, or anorthosite is the rock made up mostly of anorthite. We make these anorthosite, basically islands that gradually clump together and form a crust of anorthosite. And this ancient original lunar crust is what makes up the highlands. So this is a pretty cool story. I'm sure a lot of you are like, okay, Graham, sure. What's it like down in the lunar mantle since you've been there? I haven't actually been there. Part of the reason we know this is because the moon, as the closest body outside of our Earth, has been the most visited of everything in our solar system, right? The moon is pretty popular as far as humans are concerned. It's the only place we've put people, and we've put lots of awesome geological instruments up there, including seismometers. Seismometers are what earthquake scientists on Earth, seismologists, use to study earthquakes. But the moon doesn't have earthquakes, it has moonquakes. So when the moon rattles, we can actually figure out what the inside of the moon is made of. And the things that make the moon rattle are often things like impacts, big meteorites whacking into the side of it and making it shake.
Huh.
Cool.
Yeah, that makes sense. Are there other reasons? Like, is there still magma in its core that is also causing that movement?
Yeah, that's a great question. One that I actually don't really know the answer to. So you've kind of stumped me here. I know that the moon is still warmer inside, right? It's still holding heat inside of it. I don't think there's not a lot of geologic activity. There's no active volcanoes that we really know of on the moon.
What would we call, instead of geologic, what would we call it?
Oh my gosh.
Lunalogic?
Lunar logic. Yeah, something like that.
I like it. Yeah.
I like that. But yeah, so there's sort of just like, it's kind of this cooler body. There's no, plate tectonics going on. So it's not the earthquakes like we're used to. There's definitely no San Andreas fault on the moon. But things are always kind of settling. And every time it gets hit with an impact, right, it sort of shifts things around, and those will also kind of, reshift over time.
Can I ask you another question about your slide prior to this, the rebound one, which is like wild. I hadn't really thought of volcanoes being caused by that. Kind of like makes me think of cracking an egg or something.
Yeah, that's a perfect analogy.
Do we have some volcanoes on Earth that are made this way too?
Oh, goodness. I'm so glad you asked, Marisa. we don't have volcanoes that are forming from impacts usually, but what's happening here is a lot of what's driving this volcanism is something we call decompression melting, right? So when you whack the moon and make that crater, it blasts a bunch of material out of there. So what's driving a lot of this rebound and melting, or this melting with the rebound, is actually, it's called decompression melting. It's when you take a bunch of weight off of hot rock, it actually goes, ooh, thanks for taking that weight off of me. I'm gonna melt. And then it melts and starts like rising up through what's left of the crust. This is happening all the time in the middle of the oceans at ocean spreading centers. So the same decompression melting is what's building new ocean crust all the time. It's also kind of like what's happening beneath hotspots like Hawaii and Iceland, where you're bringing up hot rock, and once it gets close enough to the surface, it's decompressed enough for how hot it is that it starts to melt.
Okay, so it's like, it's a similar kind of process under the surface, like at the magma level. Yep. It's reacting kind of the same way, but it's just like different things happening at the surface.
Yes, right. And
that's triggering it.
Yeah, that's exactly right. And since the moon doesn't have any ocean crust that's spreading apart, it doesn't have mid-ocean ridges, the only time it gets to decompression melt is when it gets hit with a really big impact.
It'd be pretty cool if the moon did have that we could watch.
Oh my goodness. Wouldn't that be wouldn't that just be such a treat to have?
I guess it's okay that our moon doesn't do that.
Yeah, we love it for what it is. Cool. So we've talked about these two different landscapes on the moon. And so, of course, now this is the big question. Everyone wants to know, is it cheese? And the answer, unfortunately, is no. The moon is not made out of cheese. These are all actual rocks. It's not the Highlands are Swiss and the lowlands are cheddar.
Is that what you think it would be? Have you thought about this? Like, if the moon was made of cheese, which cheese would it be?
Wow. I
ask the burning questions here.
Yeah, no. This is a really important question, and it matters a lot to me as a Wisconsinite at birth. That, you know, I come from America's Dairyland. It says it on our license plate, and so for me, I love both rocks and cheese. And so I want to give this question the due thought it deserves. But for now, I think a first over, I like the idea of the Highlands as Swiss and the Maria as cheddar. Okay. But that's my preliminary answer. But
and for you watching at home, if you have suggestions, you can put them in the comments. We'd love to know your thoughts.
Okay, so unfortunately not cheese, but beautiful rocks nonetheless. So the Maria are made out of basalts. I know folks who have tuned into this are probably like, yeah, we get it. We know what basalts are by now. It's what makes up ocean crust. It's what's erupting on Hawaii and in Iceland right now. It's these, you know, dark, low silica rocks. They erupt really hot and tend to flow. Sometimes they get bubbles in them. How cool is that? The Highlands are made out of this rock that really looks a lot like granite. It's called anorthosite. It's made up of kind of similar stuff to granite, a little bit different, but you can kind of think of it as like being kind of like granite. And then this other thing, which is one of the weirdest rocks out there with a really weird name. It's called Creep with a K, K-R-E-E-P. That is an acronym for potassium, which the elemental symbol is K, rare earth elements, REE, and P for phosphorus. So those of you who might not be geochemists, potassium, rare earth elements, and phosphorus do not like to go into rocks. When you melt rocks, they're like, woohoo, we're going into the melt. And they melt. They melt with that rock and they go into the liquid. And so it's hard to get them to cool into rocks as well. And so creep formed when you have just about gotten rid of this whole magma ocean. All that's left in there are all these elements that don't play nice with rocks. And so you're just left with these pods of these really, you know, creepy melts that then erupt out of volcanoes, and those form the creep portions of the lunar crust. Very weird rocks, kind of basalt-like, but just really cool chemistries. We really don't see anything like them on Earth.
Okay, that's what I was going to ask. So why is that not something that we see on Earth? Because our magma is has a different composition, or like potassium's not in
Yeah,
there?
there are some times where you get things that we might say are kind of like creep, things that are formed in these really evolved magma chambers, right? These magma chambers last for a long time. A lot of stuff crystallizes out of them. And then what's left are these really kind of juicy, we call them incompatible melts, melts full of incompatible elements, elements that don't fit into rocks well. So we get things kind of creep-like, but creep itself is kind of special to the moon. But basalt we find lots of on Earth. Anorthosite, there are a few places on Earth where anorthosite, like big anorthosite magma chambers existed, like places like Labrador and a handful of other spots on Earth. Anorthosite's pretty rare. Creep is super rare. I don't think we see anything that's quite like creep on Earth, but we see things a little bit like it. And then another cool thing on the moon is we get breccias. Breccias are when you break up rocks and have a bunch of coarse, chunky rocks, and then you kind of moosh them together. We call those breccias. And because the moon has a lot of impact processing that's always breaking up rock and squishing it together, sometimes melting it together, we get all sorts of cool breccias of lunar material made up of mare and anorthosite creep, all sort of glommed together every time there's a big impact on the moon. So that's the cheese. That's all the dairy of it. But now what's really cool is because the Apollo missions were able to bring back all these awesome rocks to the Earth, geochemists like me and Gavin, unfortunately me and Gavin haven't actually got to work on a lunar rock, but maybe one day, got to look at these things really closely and study them really carefully. And one of the things they looked at are oxygen isotopes. And so oxygen comes in a couple different varieties. The element oxygen has a few different weights to its atoms, and those different weights we call isotopes. And that's as far as I'm going to go into this chemistry. No one tuned in here to hear me wax on about isotopes. But what we do know from oxygen isotopes is they're a great fingerprint for where things formed in our solar system. And so by looking at things oxygen isotopes, we can say if they formed close together or far apart. And if things, you can't tell the difference between them, they might be from the same place. And so this plot shows all of the meteorites and all of the rocks we've ever measured on Earth. We've gotten some meteorites from Mars, and so we know what Martian rocks are like. And then we've got all these awesome asteroidal meteorites. So things like Uralites, Lodronites, and Acapulcoites, Palisites, Angrites, the Chondrite families. Oh my goodness. Such a bounty of awesome space rocks. But these things scatter all over here, but the Earth and the moon can't tell them apart. They are so gosh darn close. And folks have spilled rivers of ink trying to suss these apart. And some folks say, ooh, they're like the littlest bit difference, but gee whiz, are they ever close? Close enough that we can say that the Earth and the moon, from a geochemical standpoint, are pretty much the same thing.
What?
Right? I know.
Wild.
This is my most exciting mic drop moment of talking about the moon, is that they're from a geochemical standpoint, they're pretty much the same thing. And that means a lot when we think about how they formed. What it means is they formed out of the same stuff. They have a shared origin. And yet, when we look up at the moon today, or worse, go to the moon, it's a miserable place to be. It's freezing cold at night. It's boiling hot during the day. There's no water to be found. It's really a crummy spot if you were to try and settle down there.
How hot does it get during the day? Do you know?
I don't know the number off my head, but I know it's hotter than boiling. And part of that is because there's no atmosphere, right? There is just pelting sunlight on the surface, and there is just frigid dark when it's away from the sun. And so it's a crummy place to live. And we look just across the way at Earth, and we've got an atmosphere, we've got water, we've got life, we've got all this stuff that the moon doesn't have. And yet they come from a shared beginning but have completely different evolutions. And so to really get at that, we actually need to think about how, let's first start with how they first formed. Because after that, they go their own ways and they have these separate histories that result in different, surfaces and what those are like, but their formation, Is it exciting? It really all started with a bang, you might say. And that is because they have the shared origin, we think that they actually formed from the same material. So what happened was a long time ago, and I'll get to exactly how long ago that was, a body called Theia, which is about the size of Mars, just comes cruising over and wallops into the side of the young Earth, and they just blast into smithereens, and they mix with each other really well. And then a moon comes out of there. And so there's this awesome animation made by a number of researchers, one of the lead researchers being Rockin Pop-Up. This is a really famous moon video. So I'm just gonna turn it on and give folks a second to watch that. And there it is, whack! The moon whacks into the side of it. You see this whole spray of stuff, and you can see these little blobs of material forming out there. And there's all this junk whirling around. And this whirls around, and it gradually starts to come together. And as all that debris out around there starts to come together, that's made of this mixture of this moon-like stuff and Earth-like stuff, of this Theia-like stuff and Earth-like stuff, we eventually get this well-mixed Earth and moon system that looks like what we've got today.
Why is it called Theia?
I don't know
where that came from.
Theia, it's a Greek, it is part of Greek mythology. I don't remember exactly who Theia was. I think Theia was a nymph, but I don't. She
came by one day and just really stirred things up, caused a scene.
Really stirred things up, quite a ruckus by Earth history standards.
And so you're saying that the Earth today, like when the Earth first formed, it was made of different stuff than what it is now, because it then became mixed up with Theia. And so now we are Earth and Theia, and so is the moon. The moon is also Earth and Theia.
Yeah.
But if it weren't for Theia, the Earth would be made up of, we don't know.
It would be a little bit different. Compositionally, I don't think our Earth would look dramatically different, but it wouldn't have a moon. And I think that would be very odd.
I don't want that Earth.
Me neither. I'm very happy with the moon we've got. But yeah, and before we really knew about how similar they were in composition, a lot of folks thought that Earth had probably captured its moon. But because they're so similar, that means it's really unlikely that we captured something from far away from the Earth. And by we, I mean the planet Earth, captured something from far away from the Earth that would look exactly like it, or that would chemically be exactly like it.
Is it at all possible for, like, while the Earth was forming, that something like the moon broke off? Like, is that a hypothesis at all too?
That has been a hypothesis that needs some pretty wild physics in play, though. You need to have like Earth forming in a really kind of funky way that planets usually don't form.
Yeah, that makes sense. So when did this happen, and how old was Earth when Theia came along?
That is a great question. Another thing that rivers of ink have been spilled over. Oops, I just started.
That's okay. We love it.
Again. And it wasn't really until like pretty recently, the last we've had a rough idea of when it all went down, but folks were really able to kind of cross the T's and dot the I's on this only in the last 10 years. And so to do this, what folks do is they find these little minerals called zircons in lunar rocks. And zircons are a geochronologist, so someone who tries to measure time in geologic history. Zircons are just a geochronologist's dream. They gobble up lots of radioactive elements that are atomic clocks, that work like atomic clocks in a geological setting. And so they gobble up things like lutetium that decays to make hafnium, and they gobble up uranium, which decays to lead. And so you've got these two good atomic clocks together. And so these scientists measured the hafnium and measured the uranium and lead and measured probably the lutetium in there. And they use all these different chronometers to really kind of tease back and make a good model for when the moon would have formed from that impact with the Earth. And they put the dot on 4.51 billion years ago. And so this was maybe only like 40, 50 million years after the Earth had first formed. So it was about 1/100th of the Earth's age was when this happened. And so the Earth and the Moon have been together for a long time. If we were to collapse all of Earth's history into 100 years, it would be 99 out of those 100.
Huh. Is this something that is at all likely to happen again? Since this happened when the Earth was relatively young, was it because like the solar system was just in a very different way back then?
Yeah, that's an awesome question, because I would also be really bummed if another Theia came swinging towards Earth.
That would be a bummer.
It would be a huge bummer. Fortunately, our solar system is a lot more quiet. It's a lot quieter than it used to be. You can only really have these big impacts like this way back when. Way back when the solar system was really chaotic, things were coming together. Remember how there are all those giant impacts, all those giant craters on the moon? Those are really old. Those only could have happened that often way back then. And so the possibility of another moon forming impact happening on Earth is as good as zero. I would definitely, if anyone tried to make a bet with you on that, I would take that bet. We're going to be okay. We're not going to have another moon forming impact. We are in a great time in our solar system to not have really big impacts like that.
That's good to hear. We can't take much more.
Yeah, no, it would be a miserable time if that was cool. So we know how old the moon is, but what about those other 4 billion years after that, 4.5 billion years? Well, the Earth and the moon have drifted apart a bit. And you'll often see, if you like looking at artist drawings of the ancient Earth, of the Archean Earth, which I know I love to do that, they always have these really kind of like goofy giant moons in the backgrounds of them. And the moon probably never looked that big on Earth, but it's definitely true that the moon used to be a lot closer to Earth. And over the last 4.5 billion years, the Earth has been pushing the moon away. It's been doing this with its own tides, actually. So most of us know that the moon pulls water and a little bit of rock from the Earth towards it. And so as the moon whirls around the Earth, or as the Earth actually spins relative to the moon, it pulls tides up and down. But that tidal bulge on the Earth also pulls and pushes at the moon. And so what happens is, as that bulge starts spinning past the moon, right? The Earth is spinning faster than the moon. So it's always kind of pulling that tidal bulge out in front of the moon. And that bulge is pulling the moon along with it. So the Earth keeps kind of spinning around and speeding up the moon like it's on like a little playground merry-go-round like that, and keeps sort of speeding it up, and that pushes it a little bit further away. So they've been drifting apart. Don't worry, we're not about to lose the moon anytime soon. The moon has been pretty close and hasn't gotten that much further away in the last 4 billion years. So I would say we've got at least another few billion years of moon.
That's good to hear too. I was just thinking too that these are kind of like forms of science illustration. What you're showing us here, that like and I have that on the brain because the museum's opening our annual exhibit of science illustration this weekend. Hint, hint to everyone watching. But yeah, I love that it's not, just looking at plants that are alive today, for instance. It's like another part of the job of those people are to take data about the ancient Earth and then turn it into this visualization so that we can like better make sense of it. Which is cool. But it sounds like you're saying that this is maybe like a bit of an extreme interpretation.
I would think that's a little bit big for the moon. Now, I wasn't there. I was not present on the Archean Earth. My guess is it's a little bit large, but definitely the moon looked bigger 4 billion years ago because it was closer.
Yeah, that would be something to see.
Yeah.
Cool. So what are we going to be talking about next month?
So the weather's getting warmer, we're getting more sunlight. It's starting to get towards that time of the year when folks love to go check out national parks and love to go to awesome natural spaces. So we thought me and Gavin, I think I see him over there. He's catching up with us now.
He'll be back in time for next month's.
We'll be back in time for next month's Rockin Pop-Up, where we're going to go through some great geologic landmarks. These are some of the famous parks and monuments and natural spaces in our country, places that folks love to visit during the summer months. And we thought we would do a nice little summer preview by looking through some awesome places, not only places, a little bit further away like Yellowstone, Arches, and Acadia, but also closer places like Yosemite and Pinnacles State Park, or Pinnacles National Park. I'm so sorry.
Yeah, National Park. I mean, somewhat new national park.
Yeah, recently a national park, but a national park nonetheless, and a great one.
Let me see if so there's like, what is this, like Arches?
Yep.
And then is this like Maine?
Yep, this is Acadia National Park.
Okay.
On the coast of Maine.
Okay, cool. And then you said, so Yellowstone, Yosemite, Pinnacles, and then is that, what's that one?
That's Carlsbad Caverns.
Carlsbad Caverns, of course. Cool. I also, we have some comments that came through, and I wanted to, in particular, share with you the cheese related.
Oh my gosh.
Yes, someone has a suggestion of stinky cheese as what the moon is made up of, which made me wonder, do you think that there is a smell on the moon? What do you think the moon smells like?
Ooh, that's a great question. I would bet, well, so there's a little bit of a trick here. In order to smell the moon, you need to be able to sniff the moon. And to sniff the moon, you need an atmosphere on the moon. But if you were to bring some moon rocks back, I think they'd smell a lot like what it would be like if you took a big old whiff. If you grabbed a nice piece of granite or a nice piece of basalt, just grab those and take a whiff of that. There's this kind of awesome smell to rocks that maybe geologists love more than the average person does. But I just think rocks have this like awesome, crisp mineral smell. It's not like rock dust smell. I know it's not good to breathe in a lot of rock dust, but it is kind of invigorating to get just that like whiff of like bare rock.
Yeah, I think, that's like sort of interesting that I know like we do invoke our senses for making nature observations a lot. Like obviously sight is one of the most utilized ones, but like you go up to a flower, you might be more inclined to smell it. Certain things make you want to touch them more. But with rocks, I think maybe because we think of them, as like these inanimate objects, like lifeless objects that maybe they don't have as much going on, but it's true. Like they have their own smells.
Yeah. And it's really true. And it's something that like, now that I'm like thinking about it, it's making me really happy because it's bringing me back to like places where I've been like out doing field work, like digging up rocks, or like, if I'm prepping rocks in the laboratory if I'm like crushing them or, separating parts of them, there's this like, this just like smell of that, like the rock. And you can kind of, if you get that dust in your mouth, you can taste it a little bit. Working with rocks can actually be a really sensory experience.
Yeah. Next time I find some basalt, I'm going to smell it and I'm going to close my eyes and imagine that I'm on the moon.
That sounds great. I'm probably going to try and do that too.
Cool. Well, I just wanted to end again I plugged the Science Illustration exhibit earlier, but I did want to just make sure that everyone watching knows that the museum, which has been closed to the public for over a year now, is reopening this weekend on Saturday, April 10th, for members only for the first week, and then to the general public on April 17th. And when you come back to the museum to visit us once again, you'll see a brand new exhibit installed, which is this year's exhibit, The Art of Nature, featuring local science illustrators. So we hope to get to see you like back in person again. It's going to be great. And so thanks everyone for joining us. Thanks, Graham. We'll see you next month for some land. I'm trying to think of a clever word. Landmark geology.
Yeah.
That's all. I can't be clever.
Looking forward to it.
All right. See y'all next time.